Okay, let's unpack this. We all rely on electricity every single day, don't we? I mean, every light we flip on, every phone we charge, every device that just hums quietly in the background, it's all powered by that, well, invisible force. But have you ever really stopped to think about where it actually comes from? Beyond just plugging something into the wall socket, how does that power truly get there? For most of us, I think it remains a bit of a mystery, doesn't it? Well, today we are going on a deep dive into exactly that, the fascinating, often hidden world of power generation. Our mission is to sort of simplify and clarify this complex world, making it crystal clear and truly accessible for anyone taking their very first steps in understanding electricity. We'll be guided by a fantastic source, Beginner's First Steps in Electricity. It explains these concepts in a way that really tries to meet you at a beginner's eye level. So you might know that electricity is everywhere, sure. But have you ever stopped to ponder the incredible, intricate journey it takes to get to you?
What's fascinating here is that while we certainly encounter electricity in nature, think of the crackle of static electricity when you rub your feet on a carpet, maybe, or the awe-inspiring flash of a lightning bolt during a storm. We see that. But the vast majority of the electricity we depend on in our daily lives isn't just found. It's actively made by humans. Our source beautifully illustrates this concept. It says, just as a diligent farmer carefully sows seeds, nurtures them, and then harvests the right fruit, humanity has learned to sort of harvest electricity. We use appropriate devices and sophisticated systems to essentially cultivate this power from various raw energy forms. And the central figure in this entire process, the fundamental machine or device, the thing that performs this critical act of creating electricity, is called a generator. It's a concept that's actually been around longer than many might realize. In fact, the world's first recorded power plant, believe it or not, was a hydroelectric facility, opened in the UK way back in 1868. And closer to home, here in Korea, electricity first lit up Gyeongbokgung Palace in 1887. And that was powered by an early coal-fired thermal generator. So it has a history. This deep dive will systematically break down the different, really ingenious ways we create electricity, starting with the big picture, then diving into the fascinating details of each method, always ensuring it's explained clearly for anyone curious about how power truly works right from the ground up.
Okay, so when we talk about making electricity, what does that really mean? How do these generators actually work? And how do we even start categorizing the huge facilities that house them? Power plants. What's the basic idea?
Well, at its heart, the entire process, no matter the specific method, it really boils down to one fundamental principle: converting one type of energy into electrical energy. That's the key transformation. Our source, Beginner's First Steps in Electricity, makes it very clear. Power plants are categorized primarily by how they achieve this transformation, specifically what initial raw energy source they tap into.
By the starting point.
Exactly. You see, the world is just brimming with different forms of energy. You've got the sun's radiant energy, the wind's kinetic energy, the potential energy of water stored up high, the chemical energy locked in fossil fuels, and even that immense thermal energy deep within the Earth itself. So each type of power plant is, in essence, a giant specialized factory, meticulously designed to take one of those raw energy forms and convert it, usually through various intermediate steps, into the usable electricity that flows through our grids.
Okay, so lots of different starting points. Where are we focusing today?
Good question. Today, we'll be focusing on the major established types, the real workhorses, you could say, the ones that consistently provide most of our power, while newer and emerging forms like bioenergy, tidal power, or other cutting-edge renewables are certainly growing in importance, and they hold a lot of promise, for sure. Our source points out that their contribution to the overall global power supply is still, well, relatively insignificant compared to these main players.
Right, so we're sticking to the big ones for now.
Exactly. This helps us focus our deep dive on the foundational technologies, the ones that underpin our modern electrified world right now, and importantly, making sure we explain them at a truly beginner-friendly level, just like our source suggests.
Perfect. So it's all about energy conversion.
If we connect this to the bigger picture, yeah. The sheer diversity of power plants we find across the globe truly reflects the incredible variety of energy forms available to us on Earth. We have everything from, that ancient stored energy in fossil fuels like coal and natural gas, to the immense power held within atomic nuclei, the kinetic energy of flowing water, the sun's light, the wind's motion, the Earth's internal heat, even the powerful rhythmic movement of the ocean tides.
It's a lot to cover.
It is. But for a beginner trying to understand how all this works, the most crucial concept to grasp is this. It's all about identifying the source of the initial raw energy, and then understanding the ingenious transformation process that takes that raw energy and converts it into electricity. And as we said earlier, the generator is the absolutely critical link in this entire chain.
The generator.
Right.
It performs that final, crucial conversion into the power we can actually use.
Mhm.
But how does that work, really? What's happening inside a generator?
That's the million-dollar question, isn't it? At its core, a generator is an ingenious device. It uses the principles of, well, the technical term is electromagnetic induction. But put simply, it converts rotational motion, or really any mechanical energy, into electrical energy. It does this by spinning a coil of wire within a strong magnetic field, or alternatively, by spinning magnets around a coil of wire. Either way works. This relative motion effectively pushes electrons along the wire, creating an electric current.
Okay, so spinning is key.
Spinning is absolutely key. So every power plant, no matter its initial fuel source, whether it's heat, water, wind, whatever, is ultimately just finding a clever and powerful way to get something big to spin that generator. That's what makes the invisible force of electricity tangible and usable in our modern lives. Without that spinning motion driving the generator, all that initial energy, whether it's heat, motion, or light, wouldn't become the electricity that powers our homes and industries.
Got it. So the whole system is built around making something spin that generator.
Pretty much. That's the fundamental goal.
All right, with that foundational understanding of how a generator creates electricity, let's now pull back the curtain. Let's look at the colossal power plants that are truly the backbone of our modern world, starting with what might be the most familiar to many of us, thermal power plants. These are often called the steam powerhouses of our energy grid, right?
That's a good way to put it. They probably conjure up images of, towering smokestacks. Though it's important to note, modern thermal plants are far more technologically advanced and, in many cases, significantly cleaner than their predecessors were. Still, the core concept remains remarkably simple.
Which is?
They essentially burn some form of fuel, typically natural gas, coal, or sometimes oil, to create something incredibly hot. And that intense heat is then used to generate a powerful force that can spin a giant turbine. And that turbine, in turn, drives the generator to produce electricity.
This is a chain reaction. Burn fuel, get heat, make something spin, generate electricity.
Exactly. A precise chain reaction of energy conversion, starting with combustion. What's truly fascinating here is the ingenious engineering behind how thermal plants transform basic heat into powerful, controlled motion and then into electricity. The process, as our source meticulously describes it, it begins with the combustion of fuel, like natural gas or coal in a large furnace or boiler. This burning generates an immense amount of intense heat.
Okay, lots of heat. Then what?
This heat is then used to boil water. But not just boil it, it creates high-temperature, high-pressure steam. Imagine steam so incredibly hot and pressurized that it becomes a powerful, almost explosive force. This superheated steam is then directed through a set of precision-engineered blades within a large turbine.
Like a giant pinwheel or fan.
Sort of, yeah, but incredibly strong and efficient. As the steam expands and pushes against these blades, the turbine begins to spin with tremendous force. This converts the steam's powerful kinetic energy into rotational mechanical motion. Finally, this powerful, sustained rotation is what the generator converts into usable electricity that can be sent out to the grid.
Okay, I think I'm getting it. Can you give an analogy?
Sure, think of it like a giant industrial-scale pressure cooker. You heat the water to an extreme degree, way beyond normal boiling point. This allows the steam to build up to immense pressure. That pressurized steam is then powerful enough to push massive turbine blades, turning that forceful push into the rotational energy that ultimately creates electricity.
That makes sense. A giant pressure cooker spinning a generator.
In essence, yes. And our source breaks down thermal power plants into three main subtypes, each with a slightly different approach to harnessing that initial heat or combustion. This allows for flexibility in how and when they're used, which is important for the grid.
Okay, what are the three types?
First, you have what's often considered the classic, most widespread form, steam turbine power plants. These are the ones that directly create that super high temperature and high pressure steam from burning fuel, just like we described. This steam is then channeled to spin a steam turbine. Their efficiency largely comes from how extreme they can make those heat and pressure conditions. The hotter and more pressurized the steam, the more powerfully and efficiently it can spin the turbine. These often serve as the stable, baseload power providers, running continuously.
Okay, the classic steam engine approach.
Right.
What's next?
Then there are internal combustion power plants. Now, these are different. Instead of generating steam externally, they directly connect an engine, much like a gigantic diesel engine, similar to what you might find on a massive ship, as our source suggests, directly to the generator. Here, the combustion of fuel, typically diesel or natural gas, happens inside the engine's cylinders itself. The force of that internal combustion directly provides the rotational motion needed to drive the generator.
Ah, so no steam involved, just the engine turning the generator directly.
Exactly. You can think of it as a massive engine, but instead of propelling a vehicle, it's solely focused on spinning a generator. These plants are often smaller in scale and can be quicker to deploy. That makes them real valuable for remote locations, or maybe as reliable backup power, or even for balancing smaller, localized grid fluctuations.
Interesting. So more specialized uses, perhaps. And the third type.
Finally, we have gas turbine power plants. In these systems, natural gas is burned directly within the turbine itself. The hot, expanding gases produced by this direct combustion jet out, kind of like a jet engine, driving the turbine to spin the generator. One key characteristic of these plants, often highlighted by experts, is their remarkable ability to start up very quickly, and they offer significant flexibility in terms of ramping power production up or down.
Oh, so they're good for quick bursts of power when needed.
Precisely. This makes them incredibly valuable for balancing varying electricity demands throughout the day. They're often referred to as peaker plants because they can kick in precisely when electricity demand suddenly spikes. So whether it's the intense heat from burning coal, creating steam, the direct mechanical power of a large internal combustion engine, or combusting gas right inside a specialized turbine, the end goal for all these thermal methods is always the same: to efficiently get that generator spinning and producing the electricity we need. They are indeed the versatile steam and combustion powerhouses that form the very foundation of our energy grid.
That's a great overview of thermal power. It really is a workhorse, as you said. Okay, so having explored the raw power of combustion, let's now delve into a source that taps into an even more fundamental level, almost microscopic, really: nuclear power. You might hear scientific-sounding words like fission or uranium. And for many, I think it can seem intimidating, maybe due to its complexity or, past associations. But we can absolutely unpack it together, break down how this incredible power is generated in a way that truly makes sense, showing how we harness what are essentially tiny, controlled explosions at the atomic level to power our homes and cities. It sounds remarkable.
It really is. And it raises an important question. How can something so incredibly tiny, like the nucleus of an atom, possibly create so much energy that it can power entire cities and industrial complexes? It seems almost impossible. The core principle of nuclear power plants, as our source clearly explains, lies in something called a nuclear fission chain reaction.
Fission chain reaction.
Yeah.
Okay, break that down for us.
Yeah. Right. Imagine this on a subatomic scale. In the heart of a nuclear reactor, a neutron that's a tiny, uncharged subatomic particle is carefully directed. It's made to collide with the nucleus of a heavy, unstable atom, most commonly an atom of uranium-235. When this collision happens, it causes that uranium atom's nucleus to split apart into smaller atoms. This splitting process is called fission. And here's the truly powerful part. When it splits, it doesn't just split into smaller atoms. It also releases an enormous amount of heat energy and, crucially, 2 or 3 more neutrons.
Ah, so the split releases more neutrons.
Exactly. And here's where the chain reaction comes in. These newly released neutrons then go on to hit other nearby uranium atoms, causing them to split, which releases even more heat and even more neutrons. This process repeats continuously and rapidly, creating a self-sustaining and incredibly energetic chain reaction.
Wow, so one split triggers more splits, which trigger more. It just keeps going.
Precisely. This ongoing, meticulously controlled fission process, as the uranium atoms continue to split, releases an absolutely colossal amount of heat energy. It's this intense heat that is the prize, essentially. This heat is then used to warm a cooling material, often just water, that circulates within the reactor's core. This cooling water gets superheated and turns into high-pressure steam.
Steam again, so it comes back to steam and turbines, like thermal power.
In many designs, yes. Just like with those thermal power plants we just discussed. This powerful, high-temperature steam is then directed to turn a large turbine. That turbine's rotational motion is what drives the generator, ultimately producing the electricity that is fed into our grids. The analogy I like is thinking of it like a set of very special energetic dominoes. When one domino falls, it doesn't just knock over one other, it knocks over multiple others. And each of those new falling dominoes does the same, creating a rapid, powerful, and continuous chain reaction that releases incredible amounts of energy. It's this carefully controlled chain reaction that makes nuclear power such a potent and concentrated source of electricity.
Controlled being the key word there, I imagine.
Absolutely critical. The profound insight of nuclear power lies in mastering this controlled release of atomic energy. This provides an unparalleled source of stable, continuous power from a minuscule amount of fuel compared to fossil fuels. Our source highlights the significant scale of nuclear power in Korea, actually. It states that 24 generators are currently operational across major power plants like Hanbit, Hanol, Wolsong, Seoul, and Gori. This gives you a concrete sense of their substantial and reliable contribution to the national energy supply, providing a large-scale, non-intermittent source of baseload power that operates independently of weather patterns.
That's truly fascinating, harnessing so much power from something incredibly small. Okay, from the fiery core of atoms, let's shift gears now, to something much more, well, serene, but equally powerful, water. If you've ever seen a powerful river or the immense structure of a massive dam, you might have paused and wondered how that sheer, relentless force can possibly be converted into electricity. Hydroelectric power plants, they're all about harnessing the simple yet immense energy of water's downfall to create electricity's rise, right? It seems like a very intuitive principle.
It really is. What's truly captivating here is the elegant simplicity of it. Harnessing one of the oldest and most fundamental forces on Earth, gravity and the kinetic power of falling water. Hydroelectric power plants generate electricity by collecting and storing vast amounts of water, typically from rivers or large lakes, usually behind a massive concrete dam. Then this stored water is released from a significant height.
Letting gravity do the work.
Exactly. As the water falls, its potential energy, the energy it possesses just due to its elevated position, is precisely converted into kinetic energy, the energy of motion. This rushing, falling water is then directed through large pipes, often called penstocks, to drive a water wheel, or, more commonly in modern plants, a specialized turbine. The force of the water pushes against the turbine's blades, causing it to spin with tremendous power, and it's the spinning motion of that turbine that the generator then converts into electricity.
So it's basically like a giant modern watermill.
That's a perfect way to think about it, just scaled up to an incredibly vast and powerful industrial level. The kinetic force of the falling water spins the turbine, and that spinning motion directly creates the power. It's considered a clean, renewable, and highly reliable way to generate electricity, simply by letting water do what it naturally wants to do, fall downhill. One of its key advantages is its ability to be dispatched quickly. You can open the gates and generate power almost instantly, especially in the larger conventional dam-based systems to respond to demand changes.
Sounds pretty straightforward.
The basic principle is yes. But there's an even more clever and dynamic version of this, a true aha moment in energy management called pumped storage hydroelectricity, which is truly ingenious, and we'll definitely dive into that specifically in just a moment. It deserves its own focus.
Okay, before we get to pumped storage, let's explore some of the other exciting renewable energy sources, the ones that are becoming increasingly vital parts of our energy mix. Let's start with solar power. When you hear solar power, you probably picture those big, dark panels, right? On rooftops or in vast fields, just sort of soaking up the sun's rays. That's usually referring to solar photovoltaic power, or PV. But I'm genuinely curious, how does something as seemingly simple as sunlight magically become electricity? Especially without any obvious moving parts like turbines. It feels almost like pure alchemy.
It does seem a bit magical, doesn't it? And this raises an important question. What's the fundamental difference between harnessing light and harnessing heat when it comes to capturing the sun's energy for power generation? They're both from the sun, but used differently. Solar photovoltaic power plants create electricity by directly converting light energy, specifically the particles of light known as photons, into electrical energy. This is achieved through a specific physical phenomenon known as the photovoltaic effect.
The photovoltaic effect. Okay, how does that work?
Well, specialized devices called solar cells, often made from silicon, are designed with layers that create an internal electric field. When light, or photons, hits these layers, it actually knocks electrons loose from their atoms within the silicon. Because of that built-in electric field, these freed electrons are then directed to flow in a specific direction. And flowing electrons, well, that is an electric current. So a solar panel is essentially just a collection of many of these solar cells connected together.
Wow, so it's a direct conversion. Light hits it, electricity flows out instantly.
Pretty much instantly, yes. It's a direct, solid-state conversion. And it's really important to differentiate this. Photovoltaic is about capturing the sun's light particles, the photons, and turning them directly into electricity. It doesn't rely on heating something up or spinning a turbine in the traditional sense. Think of those tiny solar-powered calculators you might have had. Or the garden lights that automatically turn on at dusk.
Yeah, I know those.
It's the exact same fundamental principle, just scaled up massively with huge arrays of solar cells,
Yeah.
capable of powering entire communities or even industrial sites. This direct conversion is what makes it so unique and elegant among power generation methods. However, it's also why it's known as an intermittent source. It only generates power when the sun is shining, right? So its output fluctuates with cloud cover, time of day, season.
Right. No sun, no power from PV. Makes sense.
Exactly. Which leads us to the other type of solar.
Right. That direct conversion of light is truly remarkable. But now, this is where it gets really interesting because, as you just alluded to, solar power isn't just one thing. There's also solar thermal power, and it works quite differently from photovoltaic, you said. This one is less about capturing light directly and much more about simply feeling the sun's warmth and somehow amplifying it to make power.
That's a good way to think about it. If we connect this to the bigger picture, it really highlights how incredibly versatile the sun's energy is. We can harness different aspects of it. Unlike solar photovoltaic, which focuses on light, solar thermal power plants work by concentrating the sun's heat energy onto a single point or area. They achieve this using large arrays of mirrors or lenses. Imagine fields of mirrors all angled perfectly. They effectively focus and intensify the sunlight onto a central receiver or maybe a system of tubes containing a fluid.
Okay, so focusing the heat like a giant magnifying glass.
Exactly like that, but on a massive scale. This concentrated heat is then used to heat a fluid. Often it's a synthetic oil or sometimes even molten salt to extremely high temperatures, hundreds of degrees Celsius. This superheated fluid then, in turn, is used to boil water.
Ah, boiling water again.
Yep, boiling water to create high-pressure steam. And once again,
Let me guess, that steam spins a turbine.
you got it. That powerful steam is used to spin a turbine, which then drives the generator to produce electricity. So to really emphasize the distinction, if solar photovoltaic turns the sun's light directly into electricity, solar thermal first converts the sun's heat into mechanical energy through that steam and turbine process, and then that mechanical energy is converted into electricity. It's an indirect but very effective process, relying on the sun's warmth rather than its direct light particles.
Interesting. So PV is light to electric, thermal is heat to steam to electric.
Precisely. And this method can also have an advantage: thermal storage. The heat, especially if stored in something like molten salt, can be kept hot in insulated tanks, which means the plant can continue generating electricity even after the sun has set, for several hours sometimes. That offers a degree of dispatchability or control that standard PV arrays typically lack without separate batteries.
Okay, that's a key difference. Let's move on. You've definitely seen these giants, towering windmills, gracefully turning their massive blades, often on hillsides or majestically offshore, sometimes in massive arrays, wind farms that stretch for miles across the landscape. It's amazing to think that just a breeze, an invisible force, can create so much power. But how does it actually happen? How do these elegant structures capture enough kinetic force from the wind to contribute meaningfully to our power grid?
Yeah, they are quite majestic, aren't they? What's truly fascinating here is the direct, almost intuitive transformation of kinetic energy, the energy of motion into electricity. Wind power plants utilize the kinetic energy present in the wind. As the wind blows, it pushes against the aerodynamically designed blades of a wind turbine, causing them to rotate. And these blades are often enormous. Some modern ones stretch over 80 meters in length.
Wow, 80 meters, that's huge.
It is. It allows them to capture a vast amount of wind energy sweeping through that area. This rotational motion of the blades is then transferred, typically through a gearbox housed in the nacelle. That's the boxy bit behind the blades at the top of the tower. The gearbox increases the rotation speed, driving a high-speed shaft connected to a generator. And the generator, again, converts the mechanical energy of the spinning blades into electricity.
So blades spin, gearbox speeds it up, generator makes power.
That's the chain. And our source points out a really key environmental factor in wind power. Height matters. The higher up a wind generator is positioned, the stronger and more consistent the wind tends to be. Because it's less obstructed by things on the ground, trees, buildings, hills, this means that taller wind turbines can capture significantly more kinetic energy and, as a result, produce a greater amount of electricity. This is precisely why you see these towers getting taller and taller. Engineers are always reaching higher into the atmosphere where the winds are less turbulent and more powerful.
Like reaching for better fuel, in a way.
Exactly. Think of it again like that child's pinwheel, but scaled up to an enormous size. capable of harnessing the invisible but powerful force of the wind to generate massive amounts of power for our homes and industries. Of course, like solar PV, wind power is clean and renewable, but it's also intermittent. It only generates power when the wind blows within a certain range of speeds. Too little or too much, and they often shut down for safety. That poses challenges for grid stability unless it's combined with energy storage or other flexible power sources.
Right, the variability is a factor.
Yeah.
Okay, that's a powerful visual, those enormous pinwheels harnessing the wind. Now, this next one taps into something deep beneath our feet, the Earth's own internal heat, geothermal power. It sounds like getting free, continuous heat from an oven that's always on kilometers underground. It's a less visible form of power generation than, say, a wind turbine or sprawling solar farm, definitely. But I hear it's incredibly potent and remarkably consistent.
That's generally true, yes. And it raises an important question. How do we practically access heat that's miles below us and then efficiently turn it into usable electricity? It's not trivial. Geothermal power plants work by utilizing the immense natural heat present in the Earth's deep interior. This heat comes from the planet's formation and radioactive decay. In specific geological areas, often near tectonic plate boundaries or volcanic regions, where the Earth's crust is thinner or where there are natural hot spots, this heat is closer to the surface. This creates underground reservoirs of very hot water and steam trapped in porous rock.
So you need the right spot geologically.
Absolutely. You can't just drill anywhere. The method involves drilling wells, sometimes several kilometers deep into the earth, to reach these superheated underground reservoirs. Water is then either naturally present in these reservoirs or sometimes it's injected down from the surface into the hot rock. This water gets intensely heated by the surrounding geothermal energy, often turning into high-pressure steam or superheated pressurized water. This heated fluid then either naturally rises due to pressure or is pumped back to the surface.
Okay, so you bring the heat up. Then what? Turbine time again.
Often, yes. Once at the surface, its thermal energy is used to drive a generator. In some cases, especially with high-temperature reservoirs, the high-pressure steam directly spins a turbine, just like in a thermal or nuclear plant. Very efficient. In others, particularly for lower-temperature geothermal reservoirs, the hot water isn't hot enough to make steam efficiently. So it's used to heat another fluid, one with a much lower boiling point, like isobutane. This secondary fluid then vaporizes and expands, and that vapor spins the turbine. That's called a binary cycle system.
Clever. Using an intermediate fluid.
Very clever. It allows us to use lower temperature resources. Regardless of the method, geothermal is generally considered a constant, stable, and truly baseload source of energy. As long as the Earth's core continues to produce heat, which it does reliably for billions of years, the source is there. This makes it one of the few renewable sources that isn't intermittent, like wind or solar. It can potentially provide power 24/7, year-round, making it a valuable contributor to grid stability where those geological conditions permit its development. But again, that geographical limitation is key. Not all regions have easily accessible geothermal reservoirs.
Right, location, location, location for geothermal. Okay, we've explored the constant flows of nature and the power locked within fuel and atoms. But now, here's where it gets really interesting, I think. We're going to dive into some truly ingenious systems that feel like genuine aha moments in energy engineering. Remember we talked about conventional hydroelectric power, how it uses falling water to spin turbines? Well, one of its coolest and most ingenious variations is called pumped storage hydroelectricity. You mentioned it earlier. Think of it, you said, as the ultimate energy battery. But instead of chemicals, it's made entirely of water. It sounds like a brilliant, elegant solution to a very modern problem: managing fluctuating energy demand.
It really is fascinating. What's so clever here is how pumped storage hydroelectricity tackles one of the biggest challenges in modern energy supply: how to efficiently manage fluctuating electricity demand throughout the day and night, and how to integrate those intermittent renewables we talked about. It's a specialized type of hydroelectric power, as you said. It involves two reservoirs: an upper reservoir located at a significantly higher elevation and a lower reservoir situated below it. Water is repeatedly moved between these two to effectively store and generate electricity when needed.
Okay, 2 ponds, 1 high, 1 low. How does the cycle work?
The operational cycle is ingenious and meticulously designed to optimize power generation and cost efficiency for the entire grid. Think about it. During late night hours, for example, when overall electricity demand is low, people are asleep, factories might be closed, and electricity rates are comparatively cheap. Often because there's excess power available from other constant sources like nuclear or maybe some thermal plants that can't easily ramp down. During these off-peak times, water from the lower reservoir is pumped up to the upper reservoir. This pumping process uses that cheaper excess electricity from the grid. This is essentially the charging phase of this massive water battery, storing energy in the form of potential energy that elevated water.
Okay, so charging up at night when power is cheap. Then what happens during the day?
Exactly. Conversely, during the day, when electricity demand surges, everyone wakes up, businesses open, air conditioners turn on, and electricity rates are significantly higher due to peak consumption. At these times, the water that was stored in the upper reservoir is released. It flows down through large pipes, passing through turbines on its way to the lower reservoir, generating electricity as it goes, just like a conventional hydro plant. This is the discharging phase, where the stored potential energy is converted back into kinetic energy, then mechanical, and finally into valuable electrical energy. This effectively allows the power grid to store electricity when it's plentiful and affordable, and then release it precisely when it's most needed and most valuable.
It really is like a massive liquid battery for the entire power grid.
It truly is. It charges when electricity is plentiful and affordable, and then discharges that stored energy when demand peaks. This helps stabilize the entire power grid, manage costs, and importantly, integrate intermittent renewable sources like wind and solar more effectively. When the wind blows strong at night or the sun shines brightly midday but demand isn't peak, that energy can be used to pump water uphill, storing it for later. Our source highlights Korea's significant commitment to this crucial technology, noting that there are 7 operational pump storage power plants strategically located across the country. Places like Cheongpyeong, Samrangjin, Muju, Sancheng, Yangyang, Cheongsong, and Yeshin.
7 of them. That's quite a few.
It shows how valuable they are considered for grid management. The Muju pumped storage plant, built back in 1995, offers a fantastic real-world example. Our source specifically mentions that this plant is capable of generating electricity for approximately 6 hours a day during peak times. What's even more impressive is that it repeats its pumping, charging, and generation-discharging cycle twice daily. This means that, assuming no major operational issues, it can reliably produce hydroelectric power almost year-round, whenever needed. This continuous, optimized cycling results in a much higher utilization rate for pump storage plants compared to conventional dam-based hydro plants, which often depend more on natural river flow and seasonal water availability.
That makes sense. They're actively managing the water level for optimal use. So the next time my electricity bill has different rates for day and night, I can picture water being pumped uphill.
You absolutely can. Imagine that water being pumped uphill in the darkness, getting ready to power your home and city during the demanding hours of the day. It's truly a hidden hero of grid stability and energy management.
That's an absolute brilliant system, a water battery. Who would have thought? Okay, amazing. And finally, let's talk about another immense rhythmic power source that's gaining increasing attention. The ocean's incredible, predictable power through its tides. Imagine getting electricity just from the natural ebb and flow of the sea. It often feels like a futuristic concept, maybe something from a science fiction novel. But tidal power plants are already a reality, aren't they? Harnessing the immense rhythmic energy of the ocean's breath.
They are indeed a reality, though still relatively niche compared to wind or solar. And it raises an important question. How can we consistently capture such a massive, ever-moving force like the ocean's tides? And what makes it such an attractive, promising, renewable option despite the challenges? Our source emphasizes that tidal power plants are increasingly recognized and gaining significant attention as a promising new renewable energy source. The core principle is quite clever and capitalizes on the absolute predictability of tides, which is their killer feature. Tidal power plants generate electricity by utilizing the significant difference in water levels, the tidal range that occurs between high tide and low tide, a phenomenon that happens predictably twice a day in most coastal areas governed by the moon and sun's gravity.
Twice a day, like clockwork. How do they capture that difference?
Here's how it works in detail, typically with what's called a tidal barrage system. During the incoming tide, as the sea level rises, seawater flows into a large basin or reservoir. This basin is usually created by building a barrage, essentially a dam-like structure with controllable gates called sluices across a suitable bay or estuary where the tidal range is large. As this vast volume of water rushes in to fill the basin, it passes through specialized turbines embedded within the barrage structure. These turbines spin, generating electricity. That's generation on the incoming tide.
Okay, so power comes in with the tide. What about when it goes out?
Good question. Then, when the tide recedes, the water that was trapped in the basin is held there for a period. This creates a significant height difference, or head, between the water level inside the basin and the now lower sea level outside the barrage. When this height difference is maximized, the trapped water is released back to the sea through those sluice gates. This outward flow also passes through turbines, sometimes the same ones, designed to work in both directions, or separate sets causing them to spin and generate electricity on the way out too.
Wow, so they get 2 shots at generation per tide cycle.
Exactly, because the tides occur predictably twice a day, every single day. Tidal power plants have the unique advantage of being able to generate electricity twice every roughly 24-hour cycle, once on the flood tide, once on the ebb tide. This consistent and highly predictable 2 times a day generation makes tidal power a very reliable, renewable source, which offers a significant advantage over intermittent sources like wind or solar, whose output depends entirely on immediate weather conditions and can fluctuate unpredictably. It's like the ocean itself is a giant natural piston, rhythmically pushing and pulling immense volumes of water through a specific channel to turn a massive turbine, providing consistent, clean power to the grid. The main challenges are the high upfront cost of building barrages and finding suitable locations with large tidal ranges.
Predictable power twice a day. That sounds incredibly valuable for grid planners. What an incredible deep dive we've had. Seriously, covering how our world is powered. From the unseen dance of atoms in nuclear plants and the fiery core of thermal powerhouses, to the sheer gravitational might harnessed by hydroelectricity, and the natural renewable flows of solar light and heat. The kinetic energy of wind, the ancient warmth of geothermal, and even the amazing predictability of the tides. Not to forget those ingenious pump storage systems acting like giant water batteries. It's truly mind-boggling how many different and creative ways humanity has learned to harness the energy around us to light up our lives.
It really is. If we connect this to the bigger picture, what truly stands out is humanity's persistent ingenuity. Our innovation in finding increasingly diverse and, frankly, clever ways to harness energy from our environment to meet our ever-growing needs. Each of these methods we've discussed in its own way is a testament to our continuous pursuit of progress and our growing ability to understand and utilize the fundamental forces of nature. Every time you flip a light switch or charge your phone or just enjoy the comfort of a heated or cooled room, you're tapping into one of these complex, fascinating systems, a silent network of engineering and natural forces working in harmony, meticulously designed to bring you the power you need right to your fingertips. It's easy to take for granted.
So true. So what does this all mean for you listening right now? Well, next time you use electricity, perhaps charging your laptop or turning on your favorite podcast, you might think a little differently about the incredible journey that power took to get to your device. Perhaps you'll picture the superheated steam driving a turbine, or vast quantities of water falling down a dam, or maybe sunlight striking a panel, transforming directly into current, or the tide rushing through a turbine. And perhaps it will spark a deeper curiosity, making you wonder. Knowing all these amazing ways we already generate power, what could be the next big breakthrough? The next ingenious method that changes everything about how we power our future? Fusion. Space-based solar. Something totally unexpected. Thank you for joining us on this deep dive into how we power our world. Keep being curious.